Video I am going to talk about the diffraction at a circular aperture, and using this model I am going to explain the resolving power and Rayleigh criterion. So look here, so if we have a telescope, and telescope obviously it has a lens and light. Let's say here we have an object, so light is coming from this object in all direction, but light which falls on this portion will be wasted, so only this light is converged by this lens at the screen or at the eyepiece. So basically this can be assumed as we have an aperture of circular shape. So the lens images are basically the diffraction pattern from a circular aperture or lens. So lens behaves like a circular aperture in an opaque medium. So if it is behaving like a circular aperture, then there will be diffraction effects. So diffraction effects limit the ability of a telescope. Let's see how. Since we in the previous video we find the condition for the first minima, and that was d sin theta is equal to lambda. But if we have a circular aperture, so for that this is basically d sin theta is equal to 1.22 lambda. So this is the angular position of the first minima. So it means basically you know that this is first minima and this is also first minima, and here we have our object or we have slits. So this angle is basically the angular position. So this is theta, this is theta, and this 2 theta is basically width of this central maximum. If the width is larger, then we have a, so if this theta is large, then we have a wide principal maximum. So look from this expression, so sin theta is inversely proportional to this d. So if this d, which is the diameter of the aperture, is reduced, then this theta will increase, so mean width of central maximum increase. So as a result we will have a wide central maximum, which means that we will have a wide image. So if an object is a point like, an image formed by lens will be larger. So if the diameter is large, then the image will be larger, so which is known as magnification. So now I think you have some idea about this circular aperture. So now let us talk about the resolving power and Rayleigh criterion. So resolving power is basically what? So if we have two objects that are very close to each other, so the ability of a device, an optical device, to differentiate between these two objects is the resolving power, or to reveal the finer details. So if two objects are very close, then their central maxima may overlap, because here we have one object and here we have another object. So in the lens we have a diffraction pattern for this and also a diffraction pattern for this. So if the objects are very close to each other, then this theta for the first minima will be small, and therefore the image will not appear indistinctly, because let's say this is the diffraction pattern, which is diffraction pattern is basically the image. So if this is the image of one object which is at here, and this is the image of other object which is here, so their principal, so this is the principal maxima of one and this is the principal maxima of other. So now you can see here they are overlapping with each other, therefore we cannot distinguish these two objects. So for in the telescope, in the image, these two objects will appear as a single object. So that is basically the limitation or the condition for the resolving power. Okay, so in order to explain this effect, so Rayleigh gave a criterion, and we are going to talk about this. So Rayleigh said that if the principal maximum of one image of one object falls on the first minimum of image of second object and vice versa, then the images are said to be just resolved. So look here, so this is our, let's say, one object and it has this central maximum, and here we have the first minima. So if images are such that, or the diffraction patterns are such that the principal maxima of the second object falls on the first minima of this pattern, this diffraction pattern from this object, then the images are said to be just resolved. So if it falls somewhere here, so they are not resolved. So this is basically the condition. For example, if we have principal maximum of one like this and other like this, so they are well resolved because then we can distinguish their images. But if they are taken close, so there will be a limit at which they are just resolved. So beyond that limit, beyond that angular separation, they are not resolved. So this is given by this relation sin theta 1 by 2 to lambda by d. So since we know that theta, if theta is small, then theta is approximately equal to sin theta, therefore I can write sin theta as theta. So this is basically the condition. The minimum angular separation between the between the principal maximum should be 1.22 lambda by d. So this is known as Rayleigh criterion. So the angular separation between two objects should be greater than 1.22 lambda by d. Let's say you are using a telescope and you are using the light of 550 nanometer, and you have a lens whose aperture is somehow large, so maybe you can say 100 centimeter. So for this, if you want to know the resolving power, or you want to know that which objects will be resolved, so you need to find their angular separation. So let's say this is one object, and this is one object, and this is another object, and this is our lens. So this is basically their angular separation. So if this theta, and let's say this is theta minimum, so if this theta is equal to 1.22 lambda by d, we know what wavelength we are using, we know the aperture of the lens. So if this theta is equal to this quantity, then they are said to be just resolved. But if this theta is less than this quantity, if theta is less than lambda by 2, then they are not resolved. So then they are not resolved, so we cannot distinguish their images. So that is the reason that we use sometimes we use the electron microscope instead of ordinary microscope, because this theta, in order to get more resolution, we need to decrease this. So if theta is very small, then we can distinguish very closely spaced objects. So we need to decrease this theta minimum, and it only be decreased if this lambda is decreased or this d is increased. So ordinary light have wavelength of the order of nanometers. So we sometimes we use the x-rays or the electrons whose wavelength are very small, maybe of the order of. To get more resolution, we need smaller wavelength or we need larger aperture. So that was all for this video. So thanks for watching.